All right, let's jump right in. Today, we're diving into the world of quantum computing. We've got a pretty awesome collection of sources here. It looks like you've been digging deep into all sorts of things, from the fundamentals all the way to, the potential this tech has to impact our world.
Yeah, it's pretty clear that quantum computers aren't just something out of science fiction anymore.
Right.
They're becoming real, and they're going to change how we solve problems, invent new technologies, maybe even understand the universe better. It's pretty amazing.
Absolutely.
Mm-hmm.
And it feels like we're standing right at the edge of this massive computing revolution.
It's not even just faster processors or anything like that.
Oh, yeah, it's way more than that.
It's like a completely new way to process information, like using the strangeness of quantum mechanics to solve these huge challenges that regular computers can't even touch.
Exactly. And the sources we have here really highlight that potential, how quantum computers could blow classical computers out of the water when it comes to certain tasks. Mm-hmm. One article even mentions Jörg-Owe, an expert who's been working on improving the design of these quantum processors.
Ah, yeah, Schneppat's doing some amazing work.
But maybe let's take a step back first, for those just tuning in.
Sure.
Can you break down the fundamental concepts behind quantum computing? What are the building blocks, the foundation of this revolution?
Okay, so at the heart of it all is the qubit, the quantum bit.
Okay.
And unlike the regular bits in our computers, which are either a 0 or a 1, these qubits can exist in, get this, a superposition of states.
Whoa, a superposition? That sounds intense.
Yeah, so they can be both 0 and 1 at the same time.
Wait, hold on. Both at the same time?
Yeah. It's like, imagine flipping a coin.
Okay, got it.
While it's spinning in the air, it's both heads and tails, right?
Until it lands.
Exactly. It's both at the same time until you stop it and measure it. That's superposition in a simplified way, of course. And this ability to be in multiple states at once, that's what gives quantum computers such massive power.
So it's like, instead of a computer exploring one path at a time, it can explore multiple paths all at once.
Precisely.
That is powerful.
It is.
But also probably incredibly difficult to build and control.
You're not wrong. Building quantum computers, it's a massive engineering challenge.
I can imagine.
One of the big hurdles is keeping those qubits in their quantum states, because they're super fragile.
Sensitive little things.
Well, yeah, susceptible to any kind of environmental noise. And that's actually what Jörg-Owe work is focused on. Like you said, he's been developing more robust, more stable qubits, like the fluxonium qubit.
So Schneppat's trying to make a more resilient qubit, something that can handle a bit of a shake, so to speak.
Yeah, exactly. It's like trying to build a sandcastle on a windy beach.
Ah, makes sense. What other kinds of challenges are researchers dealing with as they're trying to build these practical quantum computers?
Well, scaling up the number of qubits, that's another huge obstacle.
Because you need a lot of them.
Oh, yeah. To tackle these really complex problems, you need computers with, thousands, maybe even millions of qubits working together.
Right, working in harmony.
Exactly. But right now, even the most advanced quantum computers only have a few hundred qubits.
Okay, so there's a ways to go.
Yeah.
And that kind of leads us to the whole world of quantum algorithms.
Right.
From what I've been reading, it's not just about building the hardware, it's about figuring out completely new ways to program these machines.
Yeah. You have to take advantage of their unique capabilities.
Right. You can't just run your regular software on a quantum computer. It just wouldn't work.
Exactly. It's a whole different ballgame.
And we keep seeing two algorithms mentioned in our sources. Shor's algorithm and Grover's algorithm.
Yes, the classics.
What makes them so special? What sets them apart?
Well, they're designed to exploit the quirks of quantum mechanics to solve problems that would take classical computers, forever.
Literally forever.
Pretty much. For instance, Shor's algorithm can factor large numbers exponentially faster than any known classical algorithm.
Okay, so big numbers, factoring. Mm-hmm. What does that even mean for the average person?
Think about this. Most of our online security, for banking, emails, even national secrets, it relies on how hard it is to factor really large numbers.
Oh, so it's like the foundation of our digital security.
Exactly. But a powerful enough quantum computer running Shor's algorithm, that could crack those codes.
Whoa, that's kind of scary.
It is a concern, yeah. But that's why there's already research going on for quantum-resistant cryptography.
Okay, so a shield against the quantum sword.
Exactly, using quantum mechanics to make codes that even a quantum computer would have a really hard time breaking.
That makes me feel a little better.
Yeah.
What about Grover's algorithm then? What kind of problems does it tackle?
Grover's algorithm, that's all about searching through unsorted databases. Imagine trying to find a specific book in a giant library, but there's no catalog, no organization.
So like just piles and piles of books.
Yeah. A classical computer would have to look at each book one by one. But a quantum computer with Grover's algorithm could find it much faster.
So it's like having a superpowered search engine for, well, everything.
Right. And that could have huge implications for scientific research, data analysis, you name it.
Even AI, right? Artificial intelligence.
Absolutely. And that's just 2 algorithms. Researchers are always coming up with new ones with the potential to change, like, everything. From how we discover new medicines, to how we design materials, to how we model financial systems.
Sounds like we're on the verge of a massive technological shift.
It's really exciting.
It is. But building and programming these quantum computers, it's clearly incredibly complex.
There's no doubt about that. But people like Jörg-Owe are making incredible progress, pushing the limits of what we thought was possible.
And the field is just exploding right now.
Yeah.
The potential is kind of mind-blowing. But before we jump into all those potential applications, let's take a quick pause here. What are your biggest takeaways so far from this initial exploration of quantum computing?
Let me think. I guess what strikes me the most is just the sheer range of potential applications. Like we said, it's not just some abstract math problem. This technology could actually impact pretty much every part of our lives.
Yeah, it's not just about making things a little bit better. It's about opening up entirely new possibilities.
Exactly.
And that's what makes this so fascinating.
Agreed. It's really exciting to think about all the different ways this tech could be used.
Yeah, let's dig into some of those potential applications. One that really stands out to me is the impact this could have on, like, drug discovery and material science. How could quantum computers revolutionize these fields?
Imagine being able to simulate, like, the interactions of molecules at the atomic level.
Whoa, that's getting pretty small.
Yeah, but that's where the magic happens, right? Scientists could design new drugs with insane precision, targeting specific diseases, minimizing side effects.
So less trial and error, more targeted treatments.
Exactly. Right now, drug discovery takes forever. It's super expensive. And a lot of it comes down to, like, educated guesses. Quantum computers could speed up that process big time, leading to new treatments for diseases that, right now, we can't cure.
It's amazing to think about designing drugs at the molecular level, almost like building with, like, molecular Legos.
It's pretty wild.
What about material science then? How could quantum computing help us create new, innovative materials?
Oh, the possibilities there are huge. We could design materials with specific properties for, well, anything you can think of, from aerospace engineering to renewable energy.
So like lighter and stronger materials for aircraft.
Absolutely. Or highly conductive materials for super efficient solar panels.
That would be a game changer for clean energy. And, you know, one of our sources mentioned Jörg-Owe's work on improving the performance of quantum processors, specifically his focus on the fluxonium qubit. Could those kinds of hardware advancements pave the way for these breakthroughs in materials science and drug discovery?
For sure. As quantum computers get more powerful, more stable, they'll be able to handle more complex simulations. And that will give scientists, like, incredible insights into how matter behaves at the, like, atomic and subatomic levels. Schneppat's research is super important here because having more robust qubits is key to building those next-gen quantum computers.
So it all ties back to those fundamental building blocks.
Yeah, it all starts with the qubit.
It seems like quantum computing could also have a huge impact on financial modeling.
Oh, absolutely. I mean, think about it. Financial markets are incredibly complex. There are so many factors that influence investment decisions.
Right. And right now, it feels like a lot of financial modeling is based on, like, probabilities and predictions.
Yeah, and there's a lot of risk involved. But quantum computers could change all that. They could give us more accurate, more sophisticated models for predicting market trends, assessing risk, and optimizing portfolios.
So less guesswork, more informed decisions.
Exactly. And that could lead to, you know, better investment strategies and maybe even help prevent financial crises.
Now, that's a big deal.
It is.
But of course, with any new tech, there are always concerns.
Right.
Some of our sources brought up the possibility of job displacement, you know, like if quantum computers can automate tasks that humans currently do, what happens to those workers?
That's a valid concern, no doubt. It's something we need to address head on. Just like with any transformative technology, there are going to be changes in the job market.
Some jobs will disappear, new ones will appear.
Exactly. Some jobs might become obsolete, but new opportunities will emerge. The key is to be prepared for those changes.
So education and retraining are crucial.
Absolutely. We need to equip people with the skills they'll need to thrive in a quantum-powered economy.
So instead of being afraid of these advancements, we need to focus on adapting to them and making sure the benefits are shared widely and fairly.
I couldn't agree more. We need to have these open, honest conversations about the potential impact this tech could have on society.
And those conversations need to involve everyone, not just scientists and engineers.
Yeah, policymakers, educators, the public. Everyone needs to be a part of this. It's how we navigate the challenges and make sure quantum computing is used for good.
Speaking of challenges, one thing that keeps coming up is just how incredibly complex it is to build and program these quantum computers. Is this tech destined to stay locked up in research labs and universities, or can we imagine a future where quantum computers are more accessible to businesses and individuals?
Well, right now they're expensive. They require specialized facilities, that's for sure.
Yeah, it's not like you can just go buy a quantum computer at Best Buy.
Not yet, at least. But things are changing. Cloud-based quantum computing platforms are starting to pop up, and that allows researchers and companies to access quantum computing power remotely.
So like renting computing power instead of owning the whole machine.
Exactly. And that's a step towards democratizing this technology. Yeah, it's like renting a supercomputer instead of building your own.
Makes sense. So it sounds like cloud-based quantum computing could be a big deal, opening up access to this incredible technology. What are some other ways we could make quantum computing more accessible, more user-friendly, for the average person?
That's a great question. I mean, right now, programming these quantum computers, it requires a lot of expertise. But researchers are working on developing more intuitive programming languages, tools that would make it easier for people who aren't quantum physicists to use this tech.
So kind of like how computer programming has evolved, from writing complex code to using drag and drop interfaces.
Exactly. It's about making it more intuitive, more accessible.
So maybe one day, anyone with an internet connection and some basic coding skills could tap into the power of quantum computing.
That's the dream, right? Making this technology available to everyone so we can all benefit from it.
And speaking of benefits, let's take a step back and think about the bigger picture, the impact quantum computing could have on, everything. We've talked about its potential to revolutionize medicine, materials, science, finance. But some of our sources suggest it could even change how we understand the universe itself.
Oh, absolutely. Quantum computers have the potential to simulate these super complex physical phenomena that are way beyond what classical computers can handle.
Because they're limited by, the laws of physics as we currently understand them.
Right, but quantum computers, they play by a different set of rules.
And that could lead to breakthroughs in, astrophysics, cosmology.
For sure, even fundamental physics. Imagine being able to simulate the conditions of the early universe, or model how black holes behave.
It's like unlocking the secrets of the universe.
It kind of is, and that's what makes this so exciting. Quantum computing isn't just a tech revolution, it's a scientific revolution. It's pushing the boundaries of human knowledge, making us rethink our place in the cosmos.
It's pretty profound when you think about it like that.
It is.
And one of the articles you shared focused on Jörg-Owe work on quantum algorithms and how they could be used to enhance machine learning and artificial intelligence. Could we see, a new kind of AI emerge, one that's powered by quantum computation?
It's definitely a possibility and a really exciting one. Quantum machine learning could lead to AI systems that can solve problems that are, impossible for classical computers to even attempt.
So AI on a whole other level.
Exactly. And that could have a huge impact on fields like personalized medicine, drug discovery, climate modeling, you name it.
But of course, with great power comes great responsibility, right?
Yeah.
We need to make sure this quantum AI is developed and used ethically with a focus on benefiting humanity.
Absolutely. As we explore this incredible potential, we have to think about the ethical implications, the potential risks. It's a conversation that needs to involve everyone.
Scientists, policymakers, ethicists, everyday people.
We all have a stake in this.
It's a good reminder that progress isn't just about inventing new things, it's about making choices, setting priorities, shaping the future we want. And this deep dive into quantum computing has been, mind-blowing. We've explored the fundamental principles, the challenges, the potential applications, the ethical considerations. What are your final thoughts on all of this?
Quantum computing is still in its early stages, but it's clear that we're on the brink of something truly revolutionary. The pace of innovation is incredible. The potential applications are growing every day. It's an amazing time to be involved in this field, and I can't wait to see what the future holds.
I think you've summed it up perfectly. It's an exciting time, full of potential, but also a lot of important questions. And to our listener, I hope this deep dive has been as thought-provoking and inspiring for you as it has been for us. Remember, the future isn't set in stone. It's shaped by the choices we make, the questions we ask, the actions we take. So keep exploring, keep learning, and keep asking those big questions about the quantum world.